We're ready for chapter 5 now, which is about rational functions, fraction functions. Whenever you have a fraction function, there's a possibility that there's places where it's undefined. If there's an x in the denominator, it's very likely there's places where you're trying to divide by 0, so it's undefined. And usually what that yields is it definitely places where it's not defined, either an open circle called a hole or a vertical asymptote. So we'll be looking at that. On your worksheet, the very first sheet is kind of the rules for how to graph and what things mean. So let's just look at that real quick. If you look at it, I have the kind of a more grown-up definition of a horizontal asymptote. So it says, given a constant k, the line y equals to k is a horizontal asymptote for a function v if as x increases without bound, as x gets very, very, very big towards infinity, towards the right end of the x-axis, the y value approaches some value k. So what that means is as x gets very, very big and large, y is leveling out at a horizontal line at some value. Or as x gets very, very big and negative going that way, y is leveling out at some horizontal value. That's a horizontal asymptote, and this is how it can be talked about. This is a little bit of a hint at what we're heading towards a little bit later called limits, and which is the beginning of calculus. So, vertical asymptotes. Given some constant h, the line x equals to h is a vertical asymptote for a function v if as x approaches h, v of x increases or decreases without bound. So what that means is if x gets close to some number, the y value is either shooting up towards infinity or down towards infinity. And what you see in this little notation is as x and an arrow and an h with a little plus sign, as x approaches the value h from the right is what that means. Or as x approaches h with a little negative sign, as x approaches that value h from the left side. That's what that means. So to kind of picture this, I want you to consider this graph right here. Y is equal to 1 over x minus 2 plus 3, which hopefully you recognize this as a transformation of a basic graph. This is a basic graph. Y is 1 over x. And if you will recall, what this looks like is it's got a horizontal asymptote right here at y equals to 0, that's its equation, and a vertical asymptote right here at x is equal to 0, that's the equation of the vertical asymptote. This is, and the graph itself looks like this. It sort of hugs, oops, this gets like this. Okay, so if we think about the definitions of the vertical and the horizontal asymptotes, as x gets very, very big and positive, it's approaching this horizontal line y equals 0. It's getting very, very close to it. And as it gets very big and negative, it's getting very, very, very close to it. So this is, either one of these cases, if it got big and positive and approached the line, that counts as y equals to 0 as a horizontal asymptote. Or, separately, if it got very, very big and negative and it approached that line, both of those don't have to happen for it to qualify as a horizontal asymptote. Either one of those could make it qualify. All right, ready? As x goes to 0, when the value of x gets close to 0, what's the y doing? It's going to positive infinity. That alone qualifies x equals to 0 as a vertical asymptote. But in this case, we have the other thing happening too. As x approaches 0 from the left, gets very, very close to 0 from the left, it's shooting down to negative infinity. Either one of those would qualify x equals 0 to be a vertical asymptote, but that's what's happening. Okay, now let's have a look at this guy. This is the transformation. This is a horizontal transformation to the right 2, vertical up 3. So basically what our graph's going to look like here is going to go right 2 and up 1, 2, 3, right? So this is my new xy. This is what this guy looks like. So what's the equation of the vertical asymptote? Well, as x gets close to the value 2, it's going to positive or negative infinity. X equals 2 is the vertical asymptote. And as as x gets to positive infinity, y is approaching the value 3 in both directions. And remember, either one of those would be enough for it to qualify. All right, so that's just a picture in your head of vertical and horizontal asymptotes. Now at the bottom of this sheet, I've given you the rational function p of x over d of x. It's a polynomial over a polynomial, okay? So the degree, if v of x is the polynomial, it's like this it's a to the n, x to the n plus some other terms, over b to the m, x to the m plus some other terms. It's a polynomial over a polynomial, okay. To determine horizontal asymptotes, what you do is you compare the degree of the numerator with the degree of the denominator. And so if you look down underneath where it says vertical asymptotes, how to find the horizontal, it says if the degree of the numerator, n is what I'm calling it, if n is lower than m, then automatically you get y equals to 0. I kind of wrote myself a few of those notes right there. If it turns out that the degree of n is equal to m, then you have a horizontal asymptote and it's equal to the ratio of the leading coefficients, a sub n over b sub m. We'll look at that. If n is less than m, or if m is bigger than n, wait, I wrote this wrong. Wait, let me write this down wrong. Hang on. Where did I do wrong? When I wrote this down, I wrote this down wrong. I was writing my degrees too fast. Okay. If the numerator is smaller than the denominator, then y is equal to 0. That's what I needed to write here. If the numerator and the denominator are equal, y equals to the ratio of the leading coefficients. If n is bigger than m, if the degree of the numerator is higher, then there is no horizontal asymptote. However, if the degree of the numerator is higher than the degree of the denominator by 1 degree, an oblique exists. And an oblique is often called a slant asymptote, and that just means it's not horizontal, it's at some slant. The slope is not 0. That's all that means. All right, and how we have to find the oblique is by division. Synthetic if you're lucky, long division if you're not. So that's what we have to do. Now we're going to just get into graphing this, and hopefully some of the little, how we're going to graph it is I'm going to follow these guidelines right there, okay? And I've listed that on sheet. So find the domain. We're going to be factoring the numerator and denominator. We're going to see if there's common cancellations. We're going to be finding vertical asymptotes, horizontal asymptotes, intercepts, and we're going to see if our graph will cross the horizontal asymptote. Sometimes a graph will cross a horizontal. Sometimes it may cross an oblique asymptote. However, it will never cross vertical because it's undefined there. So that's a big deal. It may or may not cross a horizontal or oblique, but it will never cross a vertical. All right, so here we go. I think we should just start, and then we'll be answering our questions as we go. Number 1. Let's start with number 1. What I think I'm going to do, I have listed all of the problems on here. I would like to do like the first, I'd like to just shoot through all 6 of these. Let's just go find the domain. So it's a polynomial over a polynomial. Polynomials are defined from negative infinity to infinity, but when you stack them in fraction, you have a division going on. So whatever's in the denominator, if it ever equals 0, you're trying to divide by 0, and that's a problem. So the places where our domain is going to be is everywhere except where the denominator is 0. So when I go through this, I'm just going to be saying, where's my problem areas? I'm going to set the denominator equal to 0 and say, what's the problem? And avoid those numbers. So to find the domain, I'm going to say, okay, set x squared minus 9 equal to 0. I'm looking for the domain, right? And so it's not allowed to equal 0. So this will factor, right? And so the denominator is going to equal to 0 when x is 3 and negative 3. So basically the domain, x can't equal to 3, x can't equal to negative 3. All right, that's its domain. Let's go to number 2. What's this domain? Can I factor the denominator? Yeah, I can. This factors into x minus 5 times x plus 4. What if you couldn't factor it? You can solve it by quadratic formula and find out the bad values that way, or the places where it would be undefined. So I set this is cannot equal to 0, and it's going to equal to 0 when x is 5, and x is negative 4. So my domain is everybody except for X is not allowed to be 5, and X is not allowed to be -4. That's my domain. How about here? What's the domain? Does this factor? X minus 3, X plus 1, X squared minus 2X minus 3. Yep, X is not allowed to be 3, not allowed to be -1. All right, that's what I know for the first 3. We're going to go do the other ones. Let's go through and find the domain for these other guys as well. I just want to keep up my space on the board. It's important. Where is this undefined? When X is -5. Okay, so the domain here is everybody except X can't be -5. Okay, what about the domain here? Everybody except for 2. All right, what's the domain here? This will factor into X plus 2, X minus 2. Okay, so the domain here, X cannot be 2, X cannot be -2. All right, that was the domain. Cool. Let's go through and name our vertical asymptotes. Vertical asymptotes, if you look at the example of 1 over x, or the one I did 1 over x plus minus 2 plus 3, the vertical asymptote is where the denominator equals 0. X equals to 2 was the vertical asymptote when we looked at the function 1 over x minus 2 plus 3. So the vertical asymptotes come from places where the denominator is 0. So let's do this. Let's go through and list vertical asymptotes, and then we're going to talk about holes. So vertical asymptotes. All right, so, and then right after that, we're going to look at holes. All right. All right, let's look at the first one. What did we say here? This is where it's undefined, so just take the not equal to sign out of this. This is the equation, and I will definitely ask for the equation of a vertical asymptote. So let me tell you what is allowed. X equals a number is okay. VA equals to something is not okay. Just giving me a number is not an equation. That's not okay. This is how it needs to be written, right like this. The vertical asymptotes are X equals to 3, X equals to -3. That's how they need to be written. Now, what about these holes? What are they? Holes are places where instead of having a full-blown vertical asymptote where your function's freaking out and going to positive, negative, infinity, it just simply has an open circle. It just has a little bit of a hiccup there. It doesn't go crazy. Just skips over that place and continues. So how do we determine holes? Well, if you factor the numerator, and there's a common factor in the numerator and the denominator that cancel, that vertical asymptote gets a new name and it just becomes a little bitty hole. So what we're going to do here is say, can I factor my numerator? No, I'm going to rewrite my denominator into factored form, which was x plus 3, x minus 3. Okay, can I factor my numerator? No, I can't. So there's no common factors here. So these remain vertical asymptotes and there's no holes. So I'm just going to put none right there. Do not leave this blank. I'll think that you don't know what you're doing. Write none. Okay, right here. This one is basically factored. So I factored this into x minus 5, x plus 4, right? Is there a common factor here? No. These remain vertical asymptotes. X equals to 5, x equals to -4. No holes, none. All right, over here. Can I factor my numerator? Okay, this is x, x minus 3, x minus 3, x plus 1. Oh, well, we got one. Okay, what happens here? Okay, this is what happens here. The vertical asymptote is the one that's left. X equals to -1. The whole is x equals to 3. And this is going to be some kind of an asymptote, and this is just going to be a little open circle on the graph. Also, after we've figured out the domain and the vertical asymptote and the whole situation, for the rest of our project, for the rest of our graphing, we are allowed to work with the simplified version. Once we've taken care of this, we can work with that simpler function. All right, let's come down here. Can we factor the numerator? Yeah, this is difference of squares. Did we have a, oh yes, we did. This means that x equals -5 is no longer a vertical asymptote. It is just a little bitty open circle. This is the equation of the whole, and in this case, there are none. There are no vertical asymptotes. That's what happened here. And we can work with the more simplified version of our function. Great. All right, what about here? Does the numerator factor? It does not factor with real numbers, so no cancellations. The vertical asymptote is 2, no holes. What about here? Can this factor? X cubed? No, I don't know how to factor that. So no, I'm going to say no common factors. So that means these are vertical asymptote, no holes. All right. Okay, I'm about to stop this video and start and pick up again because I don't want it to be too long. But before we do, let's go ahead and finish off number 4. It's kind of a fun, unique case. What happened after we made that cancellation, we got basically a line. You can think of this as y equals mx plus b. Let's graph this line. Well, okay, this has got a y-intercept of -5. 1, 2, 3, 4, 5. Up 1, right 1, that's our slope. So we would just graph our line like this, right? Right like that, okay. All right, well, why isn't this just a line? Why did they call it a rational function? Well, it's not quite a line. It started off like this, and we got the domain is the domain no matter what else happens. X is not allowed to be -5. So over here at -5, where it goes to the function down here, let me make this a little longer. So let's see if I can keep it on the line. What happens here is as it goes down at this point at -5, what we have is it's got that little hiccup there, open circle, and that's the rest of this. So I know I have all these other little things on the sheet. What do I have? Is there a horizontal asymptote? Well, let's just look at this. The degree of the numerator, see this is now over 1, is higher than the degree of the denominator, so there's no horizontal asymptote. But it's higher by a degree of 1. So this is a little bit of a special case where it does have an oblique asymptote, but the oblique asymptote is basically this graph itself. That's how this one turned out. And the x-intercept is over here at 5, 0. Turns out, and the y-intercept is at 0, -5. Okay, I'm going to go through how to find intercepts in a lot more detail on the second part of this video, but I just kind of wanted to wrap up number 4 because it's kind of a little bit of a special case where it just turned out to be a line with a hole in it. Okay.